Hello everyone and welcome to Lecture 15. Today we'll be discussing pointwise estimators of mathematical expectation and dispersion. Here's our plan for today. We'll start with an introduction to estimation, then define point estimators. We'll cover the estimator of mathematical expectation, the sample mean, and the estimator of dispersion, the sample variance. We'll discuss important properties of good estimators, including unbiasedness, consistency, and efficiency, with detailed explanations and examples. Let's begin by understanding what estimation is. In statistics, we have a population with unknown parameters. We take a sample from this population and use the sample data to estimate these unknown parameters. For example, we use the sample mean to estimate the population mean, the sample variance to estimate the population variance, and the sample proportion to estimate the population proportion. The goal is to make inferences about the population based on the sample data. There are two main types of estimators. Point estimators give us a single numerical value as an estimate. Interval estimators give us a range of values known as confidence intervals. Today we'll focus exclusively on point estimators. A point estimator is a single numerical value used to estimate an unknown population parameter. The table shows common parameters and their corresponding estimators. We use the sample mean x bar to estimate the population mean mu. We use the sample variance s squared to estimate the population variance sigma squared. We use the sample proportion p hat to estimate the population proportion p. And we use the sample standard deviation s to estimate the population standard deviation sigma. The key idea is that the estimator is a function of the sample data. It's a statistic calculated from the sample that serves as our best guess for the unknown population parameter. The estimator of mathematical expectation, or the population mean, is the sample mean. The formula is x bar equals 1 over n times the sum of all observations. For example, suppose we have test scores of 5 students, 70, 80, 90, 85, and 75. The sample mean is 70 plus 80 plus 90 plus 85 plus 75 divided by 5, which equals 400 divided by 5, giving us 80. We estimate that the population mean score is 80. The sample mean has several important properties. It's unbiased, meaning its expected value equals the population mean. It's consistent, meaning it converges to the population mean as sample size increases. And it's efficient, meaning it has minimal variance among unbiased estimators. Now let's discuss the estimator of dispersion or variance. The population variance sigma squared is unknown, and we need to estimate it from the sample. There are two possible estimators. The first is the biased estimator, which divides by n. This is not recommended because it systematically underestimates the population variance. The second is the unbiased estimator, which divides by n minus 1. This is the recommended estimator. Why do we use n minus 1? It corrects for the loss of 1 degree of freedom because we use the sample mean instead of the population mean. This correction makes s squared an unbiased estimator, meaning its expected value equals the population variance sigma squared. The biased estimator with denominator n systematically underestimates the true variance. Let's discuss the properties of good estimators. First, unbiasedness. An estimator theta hat is unbiased if its expected value equals the true parameter theta. In other words, on average, the estimator equals the true parameter. For example, the sample mean is unbiased because its expected value equals mu. Second, consistency. An estimator is consistent if it converges in probability to the true parameter as the sample size increases. As we collect more data, the estimator gets closer and closer to the true value. The sample mean is consistent by the law of large numbers. Third, efficiency. An estimator is efficient if it has the smallest variance among all unbiased estimators. If we have two unbiased estimators, the one with the smaller variance is more efficient. The table shows that estimator A with small variance is more efficient than estimator B with large variance. In practice, we prefer estimators with higher efficiency because they provide more precise estimates. Fourth, sufficiency. An estimator is sufficient if it uses all relevant information from the sample. The ideal estimator would be unbiased, consistent, efficient, and sufficient. In practice, we try to find estimators that satisfy as many of these properties as possible. Let's examine the properties of the sample mean in more detail. The sample mean is defined as the sum of all observations divided by n. It has several important properties. First, it's unbiased. The expected value of the sample mean equals the population mean. Second, it's consistent. By the law of large numbers, the sample mean converges to the population mean. Third, it's efficient. Among all linear unbiased estimators, the sample mean has the smallest variance. Fourth, the variance of the sample mean is sigma squared divided by n. This means that as the sample size increases, the variance of the sample mean decreases. The standard error of the mean is sigma divided by the square root of n, which we estimate using s divided by the square root of n. Now let's examine the properties of the sample variance. The unbiased sample variance is defined as the sum of squared deviations from the mean divided by n-1. It has three important properties. First, it's unbiased. The expected value of s squared equals the population variance sigma squared. Second, it's consistent to harms. As the sample size increases, s squared converges to sigma squared. Third, the distribution of s squared is related to the chi-squared distribution. We lose 1 degree of freedom because we use the sample mean instead of the population mean. This correction makes s squared unbiased. The biased alternative with denominator n systematically underestimates the population variance. The bias is particularly noticeable for small samples. Let's work through a complete example. Suppose we have test scores of 6 students, 75, 82, 90, 68, 78, and 85. The sample size n equals 6. First, we calculate the sample mean, which is our estimator of the population mean. The sum of all scores is 478. Divided by 6 gives us approximately 79.67. Next, we calculate the sample variance, which is our unbiased estimator of the population variance. We find deviations from the mean for each score, square them, and sum them up. The sum of squared deviations is 301.34. Then we divide by n-1, which is 5, giving us approximately 60.27. The sample standard deviation is the square root of 60.27, approximately 7.76. Our interpretation is that we estimate the population mean to be about 79.67 and the population variance to be about 60.27. Let's look at unbiased estimators in more detail. An estimator theta hat is unbiased if its expected value equals the true parameter theta. The estimator is centered at the true parameter. The table shows common unbiased estimators. The sample mean x bar is an unbiased estimator of mu. The sample variance s squared is an unbiased estimator of sigma squared. The sample proportion p hat is an unbiased estimator of p. The biased estimator of variance divides by n. Its expected value is n-1 over n times sigma squared, which is less than sigma squared. This means it systematically underestimates the population variance. The bias decreases as sample size increases. The table shows that for n equals 10, the biased estimator is 10% too low. For n equals 30, it's about 3.3% too low. For n equals 100, it's only 1% too low. For large samples, the difference between the biased and unbiased estimators becomes negligible. However, for small samples, the bias can be significant. Consistency is another important property. An estimator is consistent if it converges in probability to the true parameter as the sample size increases. Examples of consistent estimators include the sample mean, the sample variance with n-1, and the sample proportion. The law of large numbers guarantees consistency for the sample mean. Efficiency is the third important property. Among all unbiased estimators, the one with the smallest variance is called the most efficient. The Cramer-Rao lower bound gives the theoretical minimum variance for any unbiased estimator. If an estimator achieves this bound, it's called efficient. Let me summarize what we've learned today. Point estimators are single values used to estimate population parameters. The estimator of the mean is the sample mean, which is unbiased, consistent, and efficient. The estimator of variance is the sample variance with n-1 in the denominator, which is also unbiased and consistent. Good estimators have three key properties: unbiasedness, consistency, and efficiency. We use n-1 in the variance formula to correct for bias. The key takeaway is that point estimators are the foundation of statistical inference. That concludes our lecture on pointwise estimators. Thank you for your attention.